Welcome students. So today we are going to discuss about the multi-threading model. We know that the operating system supports both user and kernel level threads, and due to this there are different multi-threading models available. So today we are going to see all the three multi-threading models one by one. So the first multi-threading model is many to one, second is one to one, and the last is many to many. So let us begin with many to one. Now, as is evident in the diagram, you can see that here many is for the user level threads. So there will be many user level threads and there will be only one kernel level threads. So in this system, many user level threads are all mapped onto a single kernel level thread. And thread management is handled by the thread library in user space, which is very efficient. The entire process will block if a thread makes a blocking system call. So as you can see here, if any one of this user level thread makes a system call. Now if you recall, what do you mean by system call? It is nothing but the interface between the process and the operating system, more particularly kernel, isn't it? So say suppose if any of this user level thread makes a system call, then what is going to happen is that if the requirement of that user level thread is not fulfilled, then system will be blocked and other user level threads will not be able to access this kernel thread unless and until that system call is resolved. So this is the drawback of this many to one multi-threading model. Now, as is seen from the diagram, a single kernel level thread is there and which is responsible for accessing the kernel at a time. And due to this, multiple threads are unable to run in parallel on multiple CPU. So this system does not permit multi-threading even if multiple CPUs are available. An example for this many to one is green threads for Solaris, and this is particularly used in the GNU portable threads. So this many to one has two drawbacks. First, entire process will block if a thread makes a blocking system call, and multi-threading is not possible even if multiple CPUs are there, as there is only one kernel thread. So let us see the next model. Next model is one to one. So here there will be one user level thread, and for that one user level thread there will be one kernel level thread. So here what happens is that here for individual user thread there will be a separate kernel thread, and due to this there is more concurrency than the many to one model, as each of this user level thread can run independently. So the first drawback that was there in the many to one, that if suppose one user thread makes a blocking system call, then other user threads will not be affected because of that. So the problem of blocking is solved in the one to one multi-threading model. And since multiple threads are there, they can run in parallel across multiple CPUs. So these were the two drawbacks in many to one. So these are resolved in the one to one multi-threading model. But there are some drawbacks. The first drawback is that there is a significant overhead, as for every user level thread you have to create the individual kernel level thread, and due to this the system eventually slows down. And due to this what happens is that many systems place a limit on how many user level threads can be created. Since creation of kernel level threads is quite a significant, the system may limit the number of user level threads that can be created in a system. So these are the two drawbacks of this one-to-one multi-threading model. Now we have seen many-to-one example. So similarly here the example of one-to-one is Linux and Windows NT or any other version from NT onwards, XP 2000. Now we have seen both many-to-one and one-to-one multi-threading model. So let us see how the drawbacks of these two models can be overcome in the third model, that is many-to-many. So here in this diagram you can see that there are many user level threads and there are many kernel level threads. So here there are, in this example, 4 user level threads and these are mapped to 3 kernel level threads. So here what happens is that many user level threads are multiplexed to smaller or equal number of kernel threads. Like in this example, 4 user level threads are mapped to 3 kernel level threads. And this number of kernel threads may be specific to a particular application or a particular machine. And due to this, what was the drawback in the earlier system, that there was limitation on how many user level threads that could be created. So that is removed in this system. So in this system, the developers can create as many threads as they consider it necessary, because you don't have to create individual kernel threads for them. And this corresponding kernel threads can run in parallel on multiprocessor. So here in this example, 3 kernel level threads are there. So they can run in parallel on different processors in this particular model. Then the second drawback of the earlier system was the problem of blocking. So here what happens is that, say suppose if some of the thread initiate blocking, then the kernel can schedule another thread for execution. So whatever was the drawback of the earlier two system, that is blocking and the limitation on the user threads, that all is solved in this many-to-many multi-threading model, and hence this is more popular than the earlier two models. So let us conclude what we have learned. So we have concluded that there are two types of threads, user level and kernel level threads. Then based on this, there are 3 types of multi-threading models. First is many-to-one. So here multiple user level threads are there which are mapped to one kernel level thread. Second model is one-to-one. Here for each individual user level thread there is separate kernel thread. And the last is many user level threads are mapped to many